So yes, I am going to present you today the presentation of Sonic, so the Hedgehog, the game we did. We are working on that for 7 years. And so let's start. Yes, so first, as I said, it makes 6 years ago, we presented at the Alchemy the first version of the game. And so it was a prototype, the reception was good, and the game was supposed to be finished like 2 years after that, but it took 6 years to complete. So I'm really happy to present that today, and it's something special for me because a lot of people that were present for the prototype, a lot of those people are still there today, and I'm really happy about that. It means something to me. Anyway, so the disclaimer. It's not a tutorial about how to program the Amstrad GX-4000. So, and also you need some technical knowledge to understand what I'm going to present. But feel free to ask if you have a question about that. So I'm not going to explain what is a ROM, an interrupt, a memory page, or something like that. Also, I did a game, I did the best thing I could do, but I'm not claiming that I did the best thing on earth. I made mistakes for sure. The implementation is sometimes not really cool, and so if you what worked for me to release the game may not work for you, but at least if you can pick some concept for your own project, that will be cool. So yes, GX-4000 actually it refers to both the console but also the Amstrad Plus. I'm not going to repeat myself on that. And yes, that's exactly what I said. So we have 100 slides today to show you. I know it's a lot, but if in the end you have like 5 slides that really caught your attention, that's exactly the goal of that. I don't expect you to copy and paste everything for your own project, but if you can return at least some few concepts, that's good. And also, so during the night, the game will be available for download. By the way, it will contain the game cartridge, but also the instruction manual and this presentation. So everyone will have access to what is going to be presented here. Okay, so this is what we are going to cover today. So the memory organization, the game loop, the interrupts, the tiles, the scoring implementation, sprite management, gameplay, collision, and general development team. So that's the topics that I think are pertinent to discuss and to present. And also it's relatively easy to discuss about that without entering too low level in the code. What is not covered with that presentation? It's the boss fight, because there is a separate game logic for that. The title screen, it's also separate, the special stage, and also my conversion tools on PC. I'm really going to focus on how to program the console and not really the pipeline that I implemented. If I would have to discuss all the topics, I promise it's a book. So, yeah. Okay, so let's start. Memory organization. So, actually the RAM on the console is made of 4 memory pages at Intel. It's what the Z80 can address. And we have 4 memory pages. So I will start with the first one. So the first memory page is used for the RAM buffer, so the video RAM buffer. It's actually made of 32 kilobytes, so it's a like to manage another scan. So it's the first part of the RAM buffer is in that page. We only need to the write access for that. So, for example, the ROM can be activated. If you write at a memory location, it will directly address the VRAM. And the lower ROM, I use that for the tags, the tags rendering. It's actually code that will be executed from there. And the same thing for the game sound FX. So I need some data at this location. So this is about the first page. The second one, as you know, the ASIC page is static. It's always at the same memory address. But when this page is deactivated, I use that for the current map data. So in ROM, I use the ROM like a storage for the map data, and I unpack that in that memory location. So I'm not going to enter too much in the detail right now, but just to let you know that we have the concept of big type sets, vertical slices that are in that memory section. After that, the third page. So that's what I use for read the RAM. So I split it with two separate sections. So the first one, it's about the different variable, the data. So there is no code in there. The global variable, gameplay variable, some temporal buffer, the DMA buffer, and the stack also. And for the code, so it's shared code, it's some helper routines that are used at this memory location. So we have the interrupt handler, the self-modifying code, the helper routine, so jump from one round to another. So it's really useful. Yeah. And finally, the last page is used also as a RAM buffer, so it's the second part of the screen. Once again, only the write access is required, so I can activate at any time the upper one. And as it's the same thing as the first page, I use that to store the tags dynamically, and I say so to switch. Everything that I can run from the ROM, I run it from the ROM, and usually it's at this location. So that's it about the memory. So the game loop. So by the game loop, the frame, so the game is running at 50 FPS. So it means we have to draw 50 frames per second. So we want to focus on how to draw one frame. And this is what I call the game loop. It's always repeating, and that's what makes the game progress. So the frame I started with, it's made of 5 big parts. The first part I totally disabled the interrupt because I need, it's where I do all the initialization, including what is related to the interrupt. So first there is the DMA buffer that is used for the music, but also to synchronize the interrupts. Also there, I am in the non-visible part of the screen, so I also initialize some registers, ASIC registers for that. I prepare some tables to start drawing the column, the row, and yeah, various in it, like I have a global front counter that I iterate. Also, very important, I set the sprite position, so I don't get artifact, I don't change the position of the sprite in the middle of the frame. We will see that later, but it's actually buffered. But I set the position of the sprite right here in that location. Next, the high-level manager. So after that, I need to manage the gameplay of the game, and it's made from there. I have the concept of scripted event list. So it allows to execute a sequence of action, and it's executed frame by frame. There is also the concept of trigger box. So when Sonic enters the box, we want to trigger a scripted event. and then what I call the map sprite. Sorry about the naming, but basically it's a way how I manage a group of sprites. But I'm going to enter into the detail later, but it's just to tell that those things are managed at this location in the frame. So after that, I have the actual columns and row drawing, so we can draw the two things at the same time. Actually, the column first, and after the row, but more on that later. And finally, some delta calculation for the next frame. After that, from there, I have the real gameplay management. So literally, we compute the sonic position for the next frame. We gather the inputs. I set there is a camera logic, so we need to center on screen sonic, for example. So everything is there about really what makes the game alive, Sonic versus the rest of the world. And after that, to finalize the sprite management, so that's at the end of the frame. It's there that I manage the rings position, so fixed one and multiplexed one. I will get back again on that later. That's where I do the sonic collision. I do the sprite refresh for the dynamic sprite. More on that later, but basically I update the content of the sprites at this location. And finally, for Sonic, the Sonic sprite also need to be updated, and I do that at this location. And I just added a note, can be iterated for new frame. It means that sometimes I don't have enough CPU, enough ZIT time to do a complete frame, and I can't complete the Sonic refresh. So I have a small detection routine that allows to try redrawing Sonic for the next frame. So it's a way to gain some more CPU time from that. Interrupts. So just to let you know about the presentation, the complex thing, it's now the second part of the presentation will be more relaxed and more easy. But now we are entering the complex thing. Yes. So why interrupts? Unlike of course we have interrupt on the Amstrad CPC, the classic version, the old version, but on the console. It's actually much more powerful. So we have different kinds of interrupts. But for the game, I use interrupt to change the background color. So it's for the first level. And also I use an interrupt to split actually the scrolling. I will get back on that later, but I need to really change the speed at unexpected lines. And also I use the multiplex ring. So it's a technique to display an array of rings, and I need to for given skyline I need to reset the position, and it's managed through interrupts. And finally, I'm not waiting after the VBN, the vertical dropping. Instead of that, I'm just waiting. I use an interrupt to detect the last line of the visible screen, and that's where my frame actually starts. And finally, I use the interrupt mode 2 and not the default one, which is the EM mode 1, because I need to get my interrupt handler at inside the third page of the memory organization. Otherwise, I would have to stick on the first page, and it's not convenient. Actually, I will get some garbage on screen because of that, and we don't want that. So yeah, I use EM2 for that. After that, so we have pre and DMA. Pre it's actually used actually the recommended use in the console to interrupt at any any visible line of the visible screen, while the DMR is originally designed to update the audio register. So the audio register, that's what made the sound of the game. And I suspect, I don't know about that, but I suspect that the DMR, the way Amstrad designed it, it's more to trigger an interrupt to feed the additional data. That's what I suspect, but we can also use those interrupts, the DMR interrupt, for anything. So we can use it actually for custom interrupts, and we are not limited to the visible screen. So I really rely on that. It's an important part of the game. Just to let you know that for Scan9 we can have a maximum of 4 interrupts triggered at the same time, but the order of call is really important. So for one Scan9, the first interrupt to be called will always be pre, then DMR2, then 1, then 0. And I really say that because I have really often what I notice with the emulators is they emulate very badly that part. Sometimes it's pre, then 0, then 1, then 2, and it was really confusing me about the score implementation. So the real order do that order. Next. So the way I manage the raster with Click, so I use that, for the first level to animate the blue sky. Actually, I have a friend, Overflow, that suggested me when I started to implement the game to use a secondary ZIT register set like what the Amstrad GX-4000 actually does. It means that I use a secondary register set just to for the color management of that of the sky. Why I do that? It's because the interrupt, when triggered, it's at the left portion of the border. So it's technical, but that allows to use the EXX instruction, then directly make LD, HL, and use the register, and basically, without too much into the detail, that allows to quickly change as a raster the color. And if I do the complete the management of iterating my counter to know the next color, it will take time, and I would lose I don't want to change the color in the middle of the screen, so about the horizontal line, and so that's why relying on the secondary register set, when the interrupt gets called, I can immediately pop the new color, and then the visible screen get the new expected color, and after that I can quickly I do the iteration to get the new color, and then I leave the interrupt. So it's a convenient way to get fast with that, and actually I don't need the secondary register set. Of course, it's used to optimize things, but I did not feel blocked by not using them. That's nice. Next, DMR interrupt configuration. So, yes, how I use the interrupt. So DMR2, I use that to play the audio register. So, and also to set, as I said, the ASIC speed. So it's used for the vertical scrolling. And I use DMR1 for the sprite multiplexing. So I use that only for the rings when of course we need to display multiplex rings. And finally, DMR0, I use that only just to trigger the end of the visible screen. And that's what I say. Actually, I'm using all the DMR, but it could be much worse. I have enough room, even with that configuration, to do more treatment if I want to do that. But I did not indeed I did not need to do that, so that's good. So yes, often we say that the console is bugged, and the reality is that yes, it's bugged, but not exactly. So actually there is a wonderful article on the CPC wiki that describes all of that, so it's there. Many people contributed to that document, so there were some research about that, but basically there is a rule that I follow for all the projects, and if you put your code that is not going to be interrupted, if you put that code in those memory section, you see it here, the console will behave exactly like you expect. It's important because when I started to implement the game initially, I completely ignored that rule. Actually, I wasn't aware about that, and I had issue. I don't exactly remember what was the bad behavior, but it's all explained in the document. Basically, you can use the console as intended without bugs if you comply to that rule. Next, tiles. So I'm going to So the tiles. We are going to start a new topic. So there will be tiles, and after that the scrolling. So first, the map orientation. The engine allows any kind of map. You can do horizontal map, vertical map, or square map. What I call vertical or horizontal. For example, this thing, it's the first level, so it's all horizontal. And this level here, it's all vertical. And this level here, it's a square or something like that. But, so we can have multiple shapes. Which space? Okay. So actually, the limit is not the width or the height of the map. The real constraint is will it fit into the memory, and really this is the real challenge, and it's not really easy to do that. So just to give you an example, this is the horizontal map, and we see that by default. So yeah, just a bit of context before I start. This is Tile. It's a software that I use to author the different maps. And when I zoom, we see it's actually a grid. And this thing, it's what we call a tile. Okay? And if I go here, we see that in the status bar, we have the size. So I'm going to be here, and we see that we have the size of the map. So for example, for the vertical 8, we have 63, so it's 64 times 8. And when I get back, this is what I show here. So that thing, if we just use that naively, we do the multiplication, and we get basically 40 kilobytes memory, and that's what I used at the Alchemy. Actually, I used back then a mix of ROM storage. This was uploaded on ROM, but you get the picture. It's not. It's a too big number. We don't want that with the memory organization that I presented earlier. So we need another approach to manage that. So I introduced the concept of big typeset. That's actually funny because I did a lot of research, a lot of iteration, and I have some data, and I tried different variations to see what is more memory efficient or not. And when I did those research, I actually observed that by doing tiles of tiles, yes, I was actually able to save memory. So just to show you here in this thing, this is, as I said here, it's a tile. Let's focus, for example, on the parent tree. So this thing here, it's a tile, but I can actually select 4 of them, and this is what I call the big tile. And this thing can be, when I store the level using this int function, the size in memory get much smaller. Actually, it reduces everything. We divide by 4. So the 40 kilobytes gets actually converted to 10 kilobytes. So it's much better. And the information to tell that a group tile, so a big tile made of 4 tiles, it's not taking a lot in memory. So now I can get all the map data in the memory page for that. So it's a good news. It's how I did. It's how I was able to get so many levels in the same cartridge. And the limitation with that, and that was a real challenge for me, is to keep the index as a 8-bit value. Otherwise, it would take more memory to store that, and it would double the size. So we don't want that. So keeping this, is it working? Right. Yeah. Battery. Ça marche. Okay, so yes, we need to keep the index with a very small value. And just a note, because of the constraints, I have to make sure that we are on the 2 tiles boundary. For example, the different clouds are at a good location. Just for that cloud, if I move it just 1 tile at the right, it will create. Again, a problem. Yeah. Okay. It will create a new group of tiles and take more rounds. So the level design is made in a way that I respect these constraints. So really, it's not that easy. I am happy for you that you see again that, but there are a lot of restrictions there. Okay, next. So this is an optimization, but to ease this presentation, you can forget that for now. Okay, but it's what I use, but forget the concept for now. What I'm going to tell, I told you that this thing was actually a tile. I'm not lying. It's the good size for the auto ring, and the tile for that is 8 pixel width and 16 pixel height. And why not 16 by 16 is because on the Amstrad, when we use the mod 0 graphic mode, the pixel is actually double sided horizontally. So working with those tiles, once again, it's a good thing. But unfortunately, it's not the right size for the engine because for the scrolling engine, we need to use something based on card tiles, and the card tile actually is 4 pixels for the width and 8 pixels for the height. So once again, we need to subdivide a tile in the program. We need to subdivide that once again with 4 card tiles. So yeah, so it makes like a poupée russe. I don't know the translation for that, but it's yes, thank you. But basically, it's a lot of system on top of other system and other system. But that's how I gain a lot of memory with that. So we display actually row and column. So we have a a big tile that is made of 4 card tiles, but when I need to display a row, for example, it's always horizontal, it's an horizontal line, and I don't need at the same time the information for the 4 card tile, only 2 card tiles of a big tile is required at the same time. And actually, I stored the different tiles on a separate ROM. So just a detail here. We see it's a text file, but basically it's the ROM organization of the cartridge. But what we see here, it's a dump of the first 8 ROM that we can use as a lower ROM. And so we see text 0, 1, 2, 3. It actually represents the 4 different zones in the game. So we have green milk zone, pink zone, and things like that. And those things are the card tiles, the data for that. So when I draw a row, I set the lower one and the upper one with the appropriate card type information, and it's actually really powerful. I know it's a bit complicated to explain that, but the Amstrad PC old generation, for example, is not able to do that, and we can with the console we are able to actually select one of the first 8 ROM for that. So if I'm not clear on that, there will be a Q&A section at the end, or just pop me to discuss that. But yeah, it really, that's the most complicated part of the presentation to explain. So the card tiles, what I call that. So actually it's not data. If it was data, to store the pixel of the tiles, first it will take, it will be optimized for the storage, but we will need to read the type pixel and then write to the viewer. And if to optimize that, we can actually avoid the read step and just write directly to the VRAM the pixel information. So it's actually pre-generated code. So just to sum it quickly, it's not data, it's really code that is executed to poke the tile information directly to the VRAM. And yeah, actually I did something that is what I think is clever. Let me check, won't be long. So this is the source code of the game, and at the beginning of each ROM there is actually what I call a jump table. So here we have all the entries of the card tiles, and we have 4 different ROM to make that. And why I'm using such a table, it's because the implementation of one tile. So what you see here is how we render one tile on screen. It has a variable size. So by relying on the jump table, I keep the same indices, and so I can always directly point to the same tile, even if the size of the implementation change. So once again, it's a bit complicated, but for me, it was really a convenient way to make my draw routine with that. Then, screen implementation. So, overall, we will first focus on the vertical screen because it was the biggest thing to do in the game, and then we will address the horizontal screen, which actually is pretty easy to do, but the vertical screen was the first challenge. So, first, what we can do with the scrolling engine in the game. So first, it's full screen. It's running at 50 frames per second. We have a max of what we can scroll. So horizontally, we can scroll 4 pixels, and for the 8, we can scroll 8 pixels, and it's in all the directions, so up, down, left, right, and it's in mode 0. So basically, it's the size of a CRT shark, you know what I mean. And when it's all optimized, it actually takes half of the CPU time, so for a frame. So it's really important to optimize that as much as possible, and that's exactly what I did in the game. So, the vertical scrolling, we will first focus on the vertical scrolling. So first, yes, it's character-based, so let's forget the concept of type, it's just about displaying characters. So, the display screen, the 8, it's exactly 256 pixel 8, so it's an 8-bit value. We use 2 VRAM buffers, as I showed you for the memory page organization, and I consider that one VRAM buffer is always 16 car 8, and so it means that for full screen we have a 32 car 8, and which means 32 car 8 means that we can actually address 256 pixels. So that's the first one, so too much complicated. So what I did with that is we actually, I have a table just to list the different address in RAM for all the character line, okay? So when there is no scrolling, so just displaying the 2 VRAM buffer, we see that it starts at the first memory page here, and then the last memory page. And as I said, there are 16 lines, so it's just the beginning of all the start address, okay? But now, if we want to scroll the pixel like 1 car 8, it means that the first character row need to be skipped. So that's what we do. We actually display the first 15 car lines of the VRAM buffer and not 16, so there is one line that is missing. And then we are displaying the 16 cards of the VRAM buffer, the secondary VRAM buffer. And then finally, because we want to scroll from one card, I display back the first row that was skipped earlier, and we draw that at the end of the screen, so totally at the bottom of the screen. And so we have 32 different use cases to split the screen vertically. So that's exactly what I did. I did 32 different entries in an array, and each entries literally tell that you need to split the ASIC split your page at this position, and then you set those values that you actually tell where the VRAM should start. So next, vertical scrolling. So yes, we have 2 VRAM buffer, but I said that we can start showing the first buffer, and then the secondary buffer, and then once again a part of the first buffer. So we actually have 3 distinct parts. The first part is just classic CRTC programming. We set the register, the appropriate register for that. And then at the same time, I actually program a split, and with the, once again, appropriate register. But we need to rely on the interrupt. We did the setup for that in the game loop to actually reprogram another split, this time for the bottom part. So I actually lied. I'm not using 32 rows, but 34 rows. So it means that I have 2 extra rows that are always hiding from the visible part of the screen. And this allows me to update, to draw the row without artifacts. So it's hidden from the drawing, so the user don't see that. So I'm using it's exactly the same concept I presented, but with 34 rows instead of 32 rows. And so I always presented about the character-based scrolling, but we can fine-tune with the console on a pixel basis and not card basis, and it's very easy to do that. It's actually a small value to set for the SSCR register of the ASIC. So now, that was the biggest part to explain for the vertical screen. If you understood that, the rest is relatively easy. So now that we have our vertical scrolling that is implemented, we can actually scroll. We want to scroll the screen left and right, and this thing is made like a classical hardware scrolling. So we just have an offset to manage, and for that when you probably remember this table where I set I tell that the beginning of the screen to copy that. To that value, I actually add an horizontal offset. And once again, the ASIC provide functionality to fine-tune to a pixel scrolling. Because when we use the classical register, of course, it's just a character scrolling. And just a small tip about that. As you know, let's say we want to put a pixel on the RAM. We have this address, and usually when we progress by 4 pixels, what we do is to use the ink, the lazy opcode to reach the location. But I always reset actually the third bit of the H, the lazy register, and that allows the screen to roll. So it's really important to do that. Otherwise, if you don't do that and that you progress in your scrolling, then there won't be the cycling won't be good, and the scrolling at some point will be erroneous. So it's very important to make sure we cycle actually the RAM buffer. So how we draw I'm going to present you how I draw the row and the column, how we draw that. So as I mentioned in the past, the tiles are actually ZIT code, so it's not data that we just copy-paste. So I need to update tables for that. So I basically compute all the VRAM address. So let's say I'm going to display a new column. I will compute all the different VRAM address of the column that I want to draw. And then I will just also I will have another table to actually enter the type we want to draw, which means we want to jump on. And just a note, an implementation note, I'm actually using the stack for that. So one address for the RAM and another address, just I actually use the red instruction to jump on the next tile and so on. I know that people that make hardware scrolling for the demos and things like that on the Amstrad CPC are used to do that. I hope. So, yeah, as I said, we use 4 separate ROM. And dynamically, I switch to the appropriate lower and upper ROM before running, because it never changes. It's always the same use case. We are always about to display the we don't need to change the ROM when we go. Okay. So I need to go fast because the batteries are going fast. So sprite management, so it's another topic. Sorry, the scrolling, the tiles and everything like that, it was hard to explain, but you get the big picture at least. You don't have the details with that, but you get the picture of, at least the direction how I implemented that. So now we are going to switch on another topic, the sprites. It's actually super interesting, and I did a lot of what I think good thing with that. So I'm going to explain. So first, the sprites, I move them at 50 images per second. So it's what makes a free animation. But as you know, with ASIC, it's slow to update the content of the sprite. I don't update all the sprites at 50 frames per second. Actually, we can update just one small portion of the sprite, and visually it still looks good. Of course, when we are used if we focus on the sprite, we notice that it's slow to update, but actually it doesn't matter much with that. What really matters is to get a very free animation, to see the sprite moving fast on screen, and that this thing moving them is really fast to do with the console. So keep that in mind. You still get good results even if the content of the sprites are not refreshed at 50 frames per second. Next, so this is how I use the different sprites. So as you know, with ASIC, we have 16 sprites available that we can render at any time. And there is the concept of sorting. It means that those sprites, actually I want to get the Sonic character always on top of the rest. So I'm using the first 2 sprites for the Sonic sprites, and then the 4 following sprites, it's for the HUD. So the HUD is actually the number displayed on screen directly on top of the view, and we want that to be displayed on top of the view, sorry. And after that, it's really important, I use 3 sprites for everything, for every enemies, for the platform, for the missile. It's just 3 sprites, and actually it's enough for that. Then we have a small ring animation. So when we pick a ring, very small animation, I'm actually using that this sprite. I use the zoom ratio to make some variation, but just one sprite, it's never updated, it's always there. And also I have a complete step of a rotating wing. I never update the content of the rings. I just set them at another position in the frame to simulate an animation with that. So that's how I use the sprite. More on that now. So Sonic, I actually update half a sprite per frame. Sonic is made of two sprites, sorry. So you see, it's really I'm really slow to update the sprite, but it still looks good. Once again, when you animate Really keep in mind this concept of animation versus the sprite content update. So after that, as I mentioned, we have the HUD rings and the HUD live. So we need to update them. Once again, we have here numbers and here numbers, but we don't need to update them immediately. I have a small routine to update when we have time for that. So yeah, I have some routine for that. So 6, 7, and 8, those sprites are used for the enemy, platform, missile, and what is really interesting is that we stream the content dynamically. So we have Sonic in the world, and I make sure that for that position we need to get, for example, let me check, maybe it will be more visual here. That's, let's say I am here, for example, let's consider that Sonic is at the middle of the screen. We will have the information to, okay, we need to display the crab at this location. So if previously we had, if we had this character, so let's say we are Sonic, I'm going to walk here, and when I'm here, we still have this content of the sprite, but then when I enter here, we have the sprite of the crab that is going to be to replace the previous content. So it's all dynamic, and what I did for that, it's an update queue. We update when we can, and only one sprite per frame is actually updated for that. So I will discuss more on that later. And yes, it's also executed at the end of the frame. So we have Sonic and also the enemies. And if if a sprite is not fully copied, the next round we will try again. And actually, I never update Sonic and the enemies in the same frame. For one frame, I will update Sonic. For another one, the dynamic sprite. So yeah. Okay, the ring rotation step. So as I said, I never touched the content of those six animation steps. So no sprite copy is done during the animation. Only the sprite position are swapped. Multiplexed rings. So what we call with multiplexed rings, it's, let me check, won't be long. So you saw nothing, I did that. So here, this thing, what we see here, this is what I call the multiplex ring. It's actually an array of rings, and it's actually a method that is often on a lot of different computers, like the C64, something like that, and it's easy to reproduce with that. So I use a DMA interrupt for that, and I just reprogram the position for the new rings. So we have an array of rings. If I get back into tile to show you, for example, this, I have the layer for the rings, and then I can select instance for one instance of ring, and we have this thing, visibility 111. It's actually a bit field, and I use the metadata property for one ring here, and I have my own commercial routine that translates all of that. But in 1 byte, I actually define a set of 8 rings as a column, and so we get just 0 and 1 to tell that the ring is visible or not. So. And I use the dimension once again to tell which ring need to be done and at which animation step. So that's what I say. Yeah, the biggest challenge here is actually the clipping with the higher part of the screen, because you see the screen here, there are rings that are hiding here, but I needed to skip those rings, but there is a clipping and it's not that easy. I remember that it wasn't that easy for me to implement the clipping on the top parts. Okay, fix the sprite copy. So this thing is actually really cool. So, as you know, an ASIC sprite it's actually 16 by 16 bytes. So it means that we have 256 bytes to represent one sprite. It's a lot of bytes. But this thing, we can't change anything about that. It's the way the ASIC is made, it's a constraint, but it's a loss of space because the value is just, we are using an indexed palette, so the values are just going from 0 to 15. That's the way it is, which means that the higher bits are not used. So what we could do is to copy the data directly from the ROM to the ASIC page. It will work, but it's a waste of space, but a waste of space, but for the storage. So I use what I call Pix2 for 2 pixels. What I do in there is to store, instead of storing 1 byte for 1 pixel, I actually use 1 byte for 2 pixels. And so it actually allows to reduce by 2 the number of sprites for the storage. So instead of using 256 bytes to represent the sprites, now we just have 128 bytes for the sprites. And the copy actually remains fast. We just have the bytes, and then we want to poke the 2 pixels in the ASIC page, and with adding data for the conversion, it's really fast to implement that. But actually, there is more. So yes, we can copy the Pix2 sprites from the ROM to the ASIC page, but since we are doing the copy operation, we can actually mirror the sprite. So we can simulate a mirror on the y-axis during the copy, which means that in the animation step of the game, you know, the Sonic, for example, is just moving to the right, but there is no move to the left animation. It's because for the Pix, the sprite, I do dynamically the flipping on the y-axis. So I save a lot of storage with that. Yeah, I was really happy with that routine. Yeah, it's not used in the game. I just use y-axis because the design only requires that. But we could also do x memory. So for all the rotation thing, we could actually have features that mimic what we see on the Master System, or all the console can actually, even the Game Boy Advance, you can switch the sprites dynamically. We can't do that natively with the ASIC, but we can simulate that. And yes, just to let you know, I also did some testing. Why not using the ZX0 data packer to unpack the data to the ASIC page. And I actually noticed that Pix2 is faster when it's optimized to do the copy. So it's actually faster to process than X0. And also, and it was a surprise for me, ZX0 is really good to compress a lot of sprites, but just for one sprite, it doesn't worth it. It's not that good, and we get better results by using Pix2. Yeah, so that's it. Okay, we get the sprite. Now the gameplay. So first, I always use world coordinate when in the game. I mean that Sonic is moving on the map, all the enemies are moving also on the map, and the concept of the position on screen, it's only at the very final, just before we want to set the sprite, the sprite gets centered to the screen. That's what I call projected position. It's like 3D. But basically, I always use world coordinate, and it's really important. Don't mix world coordinate and projected coordinate, otherwise it will be complicated to debug. And yes, so also when you want to manage a camera that follows the Sonic characters, always use the world coordinate and not the projected one. Okay, trigger box. So trigger box, it's a concept where I have an invisible box, and when Sonic enters a trigger box, we actually trigger what they call the scripted events. So you probably noticed when you play the game that when Sonic reaches a checkpoint, we have a small animation, and this is done by a trigger box. So when the character enters a box, we can trigger a sequence, okay? So checkpoints, when Sonic is at the end of the map, there is a rotating board, it's also triggered this way. And for example, when Sonic jumps on the box with the animal to release the animal, it's also a trigger box for that. So, what is a script event? It's actually a data structure. It's a set of, it's a sequence of action, and we have identifier. So basically, for one frame, I will process one command, and it's like a scripted language directly embedded inside the game. We have one instruction and with one parameter. So, for example, when I enter the trigger box, I trigger the scripted event, and for example, we can call a routine. Then next frame, we can say, hey, start updating the content of the sprite, and then automatically that will be done. And after that, you can say, hey, you can do loops. You can do what I call the once the sprite, once you know that the content of the sprite is updated, you can finally tell that, okay, you can display the sprite, it's ready. So I can wait a few frames. So it's really great because my first implementation, it was very, very bad. Basically, I had some Z80 code that waits for a counter to get a special value and then trigger that, and quickly it was super messy, and I really did not enjoy that. And so that's what I did by using an event list. That was my solution for that. And really, it's super nice because it saved me a lot of time to implement the Z80 code, and it's actually a pleasure to maintain that, to have a new event. So it's really powerful concept. So as I said, we can call for one frame a dedicated routine. We can loop the sequence, we can copy sprites, we can enable the sprite or hide them also. We can wait few frames, and really it's a powerful thing to make the game alive. So here you have an example. For example, the Dr. Eggman, when we enter the boss fight, here we see that I disable the sprite. Then I tell, hey, I want you to update the sprite. So this is my ROM where I store the data, and this is what what contains the list of sprites. And if you mix that, you know, when I said that when it's not ready, when we don't have enough CPU time for one frame, it will get delayed and we will retry to refresh the contents. All the system take that in account, so it's guaranteed that the sprite copy is done. And when the sprites are updated, when the content of the sprite are updated and ready to be used, I also call a routine with that parameter, and then I do a loop. I'm not going to explain everything, but you get the idea. So really, it's a cool thing. And yeah, a more complex thing to show when we jump, when Sonic jump on the animal box that we want to release. This is a complete sequence of events. And so yeah, because when Sonic jump, there is an animation with the button, it gets pressed, then after that it gets released, then after that we have the different explode animation on the box, then after that you get the picture, okay? And really that's what the game arrived, and I spent a lot of time on that system, but I'm really glad I did that. So don't implement don't implement gameplay code or try to be data driven with that. Map sprites, so as you know, for a sprite with the ASIC, we need to keep it at the border. We need to keep the sprites. We need to keep them, because if their position are far from the visible screen, the sprite will be displayed at another location, but sometimes it will be visible inside the screen, but you don't want that. You have your own routine for that, but sometimes you want to group your sprite together. For example, Eggman, so in the boss fight, is made of 6 distinct sprites. And when I move Eggman, I don't want to move 6 sprites one by one. All I want to do is to tell that Eggman is made of 6 sprites, and I have 1 pivot point, and I have a system that actually, for this time for the 6 sprites, check against the visible screen and do the appropriate clipping to know if we have to display or not the sprite. So once again, it's a way to simplify the management. It's very convenient. So we are still discussing about the gameplay. I found it very useful to use a very small part of the frame to rely on C, on game logic that is implemented in C. Because I noticed that quickly, even if I know how to make a test in assembly code, I find it more easier to just manage my Boolean values and do the testing, and you see all those things here. I call function. So for me, it's really easy to maintain the gameplay code. So every time, for example, when Sonic moves in the world, when there is an enemy and when Sonic jumps on an enemy and something like that, it's all managed in C for that. So just that specific part. About C, I'm not using the standard library or anything like that. I'm just using the plain C syntax. It's being converted quickly by SDCC. So the first version was slow, but nowadays it's really, really good. So in the worst case, it takes for me 10 restaurants to manage all the dynamic gameplay of the game. I know that if I would implement that in assembly code, it would be much faster, but it will be really complicated for me to maintain such code. So I'm really happy to use C for that. SDCC, actually, it's a standalone compiler. You have the C. Internally, it converts to assembly code, and it directly makes a binary file. And that's the way, for example, CPC Terroir. So it's a library from the Amstrad to make games. There are many games that are created with that, but you are still in the SDCC world. I don't want binary, I'm only interested by the C to ASM step, and I use Rasp assembler for that, so I wrote my own translator. As I mentioned, SDCC uses a weird syntax for the assembly, so I need to convert that to Rasp. And yes, as I said, I don't use the standard library. And yes, just a small tip. Don't put your parameters. Don't call function with parameters. Always use global variables. So that's the way to be fast. So of course you don't want that on modern system, but for the embedded constraints with the Amstrad, that's the way we optimize C. Okay, collision. So another topic. The collision, so Sonic versus the enemy, we rely on simple collision boxes. So we first update the position of Sonic, then okay, what are my enemy currently on screen, and it's really easy. Sonic has a bounding box, and the enemy has a bounding box, and we actually try to collide them, and then we take a decision. If Sonic was jumping or was in rolling ball mode, then the enemy dies. Otherwise, it means that the enemy is actually touching Sonic, and Sonic was walking. In that case, Sonic is dying. Okay, so it's not complicated. It's easy to understand, and it's really fast to implement. The rings, it's the same concept. Okay, when we have rings, Sonic touch a ring, and that's good. But this thing was super complicated. Naively, I thought that to test Sonic against multiplex rings, we have a lot of rings to test. So my first implementation was very naive. For every rings, I tested the actual Sonic character, and it was super slow. That was my first test, and it took me like 40 Wasserman to do that. So I did another approach than that. And my solution was, since, as I said, it was the rings, the multiplex rings are actually an array. What I try to do is, to compute the Sonic position in that array. And so by using that, I have just one ring to test in that array and not the complete thing. So I was happy to find that solution, and that it worked. So that's what I did. Sometimes it's not super cool. Sometimes we have the feeling that we miss the rings, but by playing it, I decided that it was fine. Yes. Collision. So I mentioned the collision so far with the rings, with the enemies, but Sonic versus the ground, the terrain, it's actually another algorithm. What I did, that was my first implementation, and I always keep that. So it was in my first prototype demo and things like that, and I think it worked for me, so I continue to use that. So basically, for X position in the world, I just get the elevation for that. I'm going to explain that visually. So yes, here you see it's the first map. So we have like an horizon. We have this is the corresponding tile set that I'm using. So I'm going to switch back. This is the map. This is the used tile set for that map. And for that tile set, now I'm going to show you a collision mask. So for example, if we focus on that part, I don't know if you see my cursor, but if I switch there, you see that the same tile information, and that's how I do the collision. When we have the green color in the tile set, it means, okay, it's the ground and Sonic can't enter into it. And that's how I do my detection, for example, with the spikes. We know that when Sonic touches a spike, it dies. And actually, I'm going to check the tile. Okay, we are on the red tile, so it means that Sonic will be dying when in contact. So really, it's easy. And this is the final result. If I get back to the map, what the players see internally, this is what we get. So it's the game. We can you understood the concept. And of course, I don't store that big map. Let's say we have 100 tiles horizontally. I just store the Y information with the die information. But actually, I'm a bit more clever than that. The engine allows 3 different levels. So that's what allows to make a tunnel, for example, of level. But that's the big concept. I did improvement on top of that, and also with the memory organization. But yeah, that's how I did the collision versus the ground. Now, that's the fun part of the presentation. So, general development tips. Just a disclaimer, it's a personal opinion. Maybe you will disagree with that, but that's my opinion. Okay, forget the VBL, vertical marking. So that's what I actually mentioned earlier in the presentation. Don't wait for the VBL. Try instead to get the last visible line of the screen, and this is your new frame. It's important because it means that you will have more time where before the visible screen, so you can do more in it, and so it's really a critical part of the frame. So the more you are spending time there, the best it is. Sprite update versus rustering. Yes. When you update the content of a sprite, and that it's actually being on the same line that the Canon beam, you will notice some white artifacts. And I can't do anything about that. So I try to reduce the impact of the artifact. If, for example, Sonic is on the top of the frame, it will be easy to see those white artifacts. But I put the camera at a location where it's always stuck on Sonic at the bottom of the screen, so there is nothing like that. By the way, it's to my knowledge, okay, the white artifact. I don't know if it's simulated. Maybe there are new emulators that simulate that. But keep in mind this thing: you can't update on the same raster line without having those artifacts. And it was a surprise to me because, as I said, the emulator wasn't supporting that. And when I played the game, the real hardware, then I saw those artifacts. So, context for item sprite. Yeah, that's funny, but for example, you have a sprite, and if you set a value of -80, the sprite gets hidden. But you can put any kind of value. So you can say that 79 minus is also a possible value, something like that. And that allow to put some context on how you decide to hide your sprite. For example, yeah, just get this in mind. It's because when we pause the game in an emulator, we can get those values of, for example, the position, and it gives a context how the sprite got hidden. So sometimes it's convenient. And also this could be pause Y or thing like that. You get the idea. Controller schemes. So this thing is that was suggested to me by Toto, I think. But we want to make an action. For example, we have button 1 on the game controller to make Sonic jump, but we have also the Z key, and we have also the control key. So my first implementation was to test all those keys to trigger the jump action. But instead of that, it's very slow on the Amstrad to test the status, the press status on a key. So instead of that, we actually let the player to select his own controller scheme. For example, when we are in the title screen and that the player wants to start to play the game, it press, for example, the button 1 on the controller, and because we detected that, it means that, okay, the whole game will rely on that button, so it will use the controller scheme, the controller scheme, and not the keyboard or something like that. And really, it saved me a few raster lines with that, and it's a good tip for that. Determinist timing, yes. The game is totally determinist. It means that if you play the game one time, stop it, and replay once again the game, you will get the exact same animation, the same step. It will be identical. And so what I did for that, I don't have separate counters to rotate the animation step or thing like that. All I do is to maintain 16-bit frame counter, and after that I can access that frame counter as a 8-bit value if I want, or I can, that 8-bit value, I can make an AND operation for that to get a smaller value. And basically, using one counter for everything simplified the implementation, and it's actually also an optimization. So, and yes, it guarantees to get always the same in-game experience. Shadow sprites. So as I said, never directly update the position of your sprite in the middle of your frame. Instead, use a separate array in RAM, and at the beginning of the frame, just set your position at the beginning of the frame when the screen is not yet displayed. That's the good location to update your sprite position. So no visual glitch, and yes, it's cleaner. Configuration file. So don't hardcode values in your implementation. It may seem obvious, but I use separate config files for that. So one global config file, one game config file, and one bonus. It's actually the special stage, and so it's easy for me to get to tweak the game just by opening one of those files. So not everything needs to be optimized. We are not making a demo, it's a game, and we need to identify which part of the game is slow to process, and that's where what you need to focus on you need to optimize only what really takes time, and that's what I did with Sonic. So I optimized the drawing of the column, and I did my thing with the sprite updates and things like that. And because I did that, all the rest of the implementation is, I believe it's good ZAT implementation, but I did not optimize a lot this code. And yes, that's what allowed me, for example, to use the C implementation for the gameplay. Yes, and drawing configuration also are slow, so you have to think about managing the update of your sprites in a clever way. European says. So this applies to the game I did, but also for the demo that I created in the past. The first implementation you do is not good. The second one won't be good too. What I mean with that is don't get blind with your first implementation. Maybe you can perfect it, and that's totally fine to remove some old code, or even if you spent weeks on that, be results oriented. What matters is what you want to target, and sometimes it means that you need to rework everything. So really, I insist on that, because sometimes it's a trap. You get something visually on screen, and okay, it's cool, but still you have some rooms for improvements, iterate, and the improvements may not be only visual, but with the implementation, with optimization, and things like that. And also, yes, good design sex. With the modern programming, sometimes we have a good design, we want reusable code, we want an routine that we can reuse in several different contexts, variables that are all well organized. So I'm kidding, writing that hey, I'm doing some object-oriented code in ZAT assembly, or it's totally data-driven, or I work unit tests. And those things, we all agree that it's a good design, but it's a trap. Actually, with the ZAT, we often rely on self-modifying code, on using global variable. Sometimes we need to include assembly files directly in the implementation of other assembly files. We need to rely on code that is pre-generated, or we need to rely on code that is not interrupt friendly, or we need to repeat the code, or we need to waste memory to allow more optimization. So my point is that I believe that a good design in the modern days is not compatible with when you apply heavy optimizations. Benchmarking. So of course I use the emulator to get the precise timing of a routine, but I still rely on the good old raster lines just to monitor how much it takes visually. So it's not really accurate, but it gives me an idea of which system is currently taking time in my frame. That's how I made sure that I was still good with the timings. Naming convention. So it's only, that's a convention that I applied for the implementation in Sonic. I noticed that it was better for me to actually tell the type of the variable. So I use a prefix, B for byte and W for word, and so I know that I should access, how it actually matters for me to know how I can access the value. So it's exactly the same thing in terms of memory or something like that, but when you rely on that, because I have a lot of variables, and sometimes I can forget the size of those variables. So using that, it was a good thing for me. And yes, so we have Sonic is a game for the GX console, and we want you want the code to be run from the ROM, and you want to minimize the impact on the RAM, the minimize of the code you put in RAM. And so I decided to use the RAM prefix, so in front of all the function or data or things like that. And for me, it actually saved me I know where the data, where the code goes with that. So for me, it was a very practical guideline. Data structure. So RASM provides support for structures. At first, I did not use it, but I highly recommend to use it. I don't use much. Actually, I use a structure for what I call the global variant. So at any time, this thing is in RAM. But I also have the game variables and the bonus var. It's for the special stage. And all of that are put in a separate structure. And why I do that? What is cool with that? So global variable, I put in there the life count, the count level, so the game progression. But game var, it's, for example, it's related to the current game we are playing. But when I play the special stage, I don't need to get the variable of the main game. I mean, I'm only interested in having the global variables and the bonus variables. It was really an important concept for me because, as I mentioned, I have a lot of variables and it really starts to have an impact with the memory usage. So just relying on global var and the big point with that is that the game variable and the bonus variable actually share the same memory location in RAM. So you understand why I did that. Yes, so I have a workflow. So of course I use the source control, I use Git to manage my implementation, and usually, because I got a comment on the CPC Wiki forum that I should never store binary data in my change list, but I don't care. For every commit, I actually always push 2 files. First, I have a file that describes the cartridge memory layout. So that's what I showed you here. This thing, it's a test file, and I push that file with every commit. And that's allowed to make a diff, so I know exactly what to change in the memory, in the RAM cartridge. And also, and that's really important for me, I actually push with the change list the CPR, so really the cartridge file. And it was really precious to me to chase regression because sometimes I got some regression, and to find which change list was my issue, it was really complicated. For example, just let you know this emulator, so it's a GTK front-end of the CPC EC emulator, and I monitor the CPR, the cartridge file. So I can switch back to a previous change list, and then it will update locally the CPR file, and then it's easy for me to test the new version, to test the current version in the emulator. So it allows me to find the regression. So it worked for me. I'm not telling that it will work for you, but for me it was good. So yeah, that's what I say. Result of a build, so that's the test file I mentioned. So I get the diff for that. And so it's an example of diff. Here I just change some data, and I see that it took it took 256 bytes for that. And closing word, we are almost done. So it's more just to let you know that before Sonic we made several demos, and the film demo, it took us 9 months. For 10, it took more than that. And then PHX, that was released at the revision, it took 5 years, and Sonic 7 years. My point with that is it's totally fine to spend years to develop something. My experience is that usually provide better results than doing small iterative production. It's my opinion. The Amstrad machine, we are talking about machines that are 40 years. There is nobody that is waiting after you. I mean, it's just a hobby. It's perfectly acceptable to progress slowly. For example, Sonic may seem impressive, but honestly, sometimes I just spent 30 minutes in a week. Sometimes I was in vacation and I did much more than that. What I try to do is to make a routine. What I did in the last years was to actually go every Saturday in a cyber cafe for 3 hours, so in the middle of students. And it was like a mental app for me to get productive. So yeah, try to make a habit, progress slowly, it's totally fine, but don't rush things, just iterate, and at one point you will be done. And yes, of course the target, as I said, the more it's polished, the better reception will be. We have many projects here, wonderful projects, and I'm thinking about Double Quest, Brussels Goblins, Vespertino, I don't know. Those projects are there for years, and the result will be much better than a small homebrew release in 2 weeks. Okay, just to finish the presentation, there are 3 important documentation that are available online. What I used, it's actually it's available. Everything is available on the CPC wiki. There is that doc from Amstrad that describes how to program the ASIC. It was updated later by executioner and Arnaud. They gave some additional clarification about that. But really, I still remember that I read that doc, and I read it again, and I read it again, till it was not clear to me. Everything is there to know how to program the ASIC. If few things are not clear, so you read it again, till you understand the concept. But focus on that. It's really the Bible of the ASIC programming. The bug about the interrupts that I mentioned earlier in the presentation, everything is explained here, and read it. It's the way to use the console without bugs. And finally, it's a PDF that is also available on the CPC wiki. I use that doc really often and for years. It's the log timing of every ZIT instruction, and you usually want to use the instruction on the left thing. That's what when I try to optimize code, I always get this PDF file open. And one last thing, there is also a nice tutorial from Arnaud that describes how to use the ASIC. There are animated GIFs, to explain the concept, and I advise you to have a look on that. It's really good. So we are done. I'm going to make a few thanks. Gerald. So Gerald is the creator of the C4 CPC cartridge, and everything that we do, if we are here today to discuss about the programming with ASIC, it's only because we are able to test the code on the platform, and we have to thank him for that, for this thing. I really hope there will be alternative in the future, because we need new boards to be created. But really, let's not forget that. After that, yes, Toto, Rad, and Nemocontio, they tested the game this summer a lot, and I want to thank them for that, because testing is not always fun. Sometimes you have to retest and retest and retest again the same thing, and it really helped me, and also having some that could be actually an advice when you make a game. Try to have some friends that you know you can trust them to not release the game, and get some feedback, and try to really listen to what they say, and sometimes they are suggesting you enhancements that are really important that you don't know. Maybe just for example, one example about Toto. When I created the special stage, my initial goal was to make a clone of the Trailblazer game. So Trailblazer, it's a chessboard that is progressing, and you have some holes, and I wish to make a clone of that game, so using Sonic as a ball. That was my intent. And when I sent the first preview to Toto, he actually told me, yes, it's good, but where are the rings? And I did not expect that answer. I did not think at all about adding rings on top of the chessboard, and so for the special stage, and it improved the games and many things like that. So thanks also for Targan for the audio. I believe there is a fantastic work in there. Targan, it's not only about creating the music, but it's also the player routines. I had to adapt them for the ASIC, for the demo buffer, but otherwise it was really super good. So good work. Same also for the graphics conversion. I did not mention that, so yes, we took the typeset of the Game Gear version, so it's also the same that the Master System, and what we did is actually to take those tiles and to resize them vertically. So the tiles in Sonic GX are actually twice higher than the Master System one, and Seth did all the magic to make it great, and that I believe that the final result is really much better with his work. And also said he's a good magician, because sometimes I ask him to reduce the sprite. You know, I mentioned that we were using only 3 sprites for the enemies, and sometimes the original sprite it was made of 4 sprites, and sometimes even 5. And he was able to shrink that in only 3 sprites. And when you see the sprite, okay, it's really, really well done. Slipe also, so he is author with Wide and Two of the CPC Funds BZH. It's a French magazine, but I asked him on the very last minute to create an instruction manual for the game, and the result was unexpected. Actually, we have super good documentation. Just to show you that, it will be quick. This is what Slipe did for us, the complete instruction of the game, that if we print it, it's actually the size of an original box of GX box. And I'm really super happy about the results, so thank you a lot. And finally, getting back to where is my presentation? Okay. Yes, here. Thank you, a big thank to Overflow, especially Overflow for the technical discussion that we got at the beginning. It was before the HMI, but it helped me to improve, especially with the vertical scrolling. My initial intent was to use two separate buffers, and so it will mean that I will have to draw two separate rows, and because he suggests me to only update one row, and so that's he changed the whole game with his advice. So thank you a lot, Overflow. And finally, yes, thank you a lot to the people from CPC Wiki, from CPC Rules, and the whole Demoscene community. It means a lot, at least to me. I'm making this game for the community. The community made great game in the past. I'm thinking about R-Type, I'm thinking about Pinball Dreams, and all those great games, and they were free. And today we are releasing Sonic exactly in the same fashion, and I'm really with that. There is a trend to sell games, homebrew games, and I don't think it's a great way to go. So keep your games free, and that's nice. And yes, that's it. Game over.
Yeah.
Q&A session, if you have questions, do not hesitate. We went through 100 slides, and really we did it.